Okay, welcome. Uh, Today we're going to discuss one-sided limits. So last time we discussed general limits. So learning objectives are following. So I will tell you roughly definition of limit when sort of x approaches from one side, from right or from left. And then we also discuss how to compute the limit of sine theta over theta or those kind of things. Okay, now uh, it might happen that limit may not exist, right? We saw some examples where limit doesn't exist. However, uh, right limits or left limits may exist. So when you approach from left, when you approach from right, it may exist. So it's somehow meaningful to introduce these notions, right? Um, so basically, what I say is limit as x goes to c, where I add plus, so which means from right, f of x is equal to L means, it means what? So it means uh, we can we can make we can make f of x uh, as close to L as we want by doing what? By making making x very close to c, right? So if I do this, this becomes just a limit. But what I do is with x being bigger than c, okay? So I'm picking x slightly bigger than c, okay? So this is a right hand limit. And similarly, you can also say limit x goes to c from minus means it's from left, f of x equal to L, it means, so let me just do this. So this is like if and only if, it means uh, f of x is very close to L if x is very close to c, but x is less than c, okay? So that's kind of a shorthand of writing all these things, but let me also explain with pictures. So what might happen is like in one example, but anyway, so let me do a step function x and y. Oh, sorry, this is x and this is y. Okay, let me pick a different color. So let's say that I have some sort of a step function here. Here's my c. Let's say that I'm right here. Let's say that 5. Let's say that here this is, let's say that 2, and here's my function. Function looks something like this. Okay, so this is a step function, right? If you want, I mean, you can also define it in the following form. So it's either 5 or 2. So it's 5 if x is bigger than some point c and it's less than c. So c is some value, I don't know. So what happens then if you look at this limit as x goes to this point c from positive side? So positive side means you're approaching from right. Okay, if you approach from right, what is your function? So your function is here, right? So you're approaching to this point 5. So then your f of x is simply 5. Now if you were to approach from left, right, here is the left. Let's pick a different color. So if you're approaching from left to c, then your function, here's your function, right? You're approaching to that point, but this point is just c, right? Y-axis. So this is your f of x. That would be just 2, or c. So both limit exists, right? We found the answer. One is 5, the other one is 2. But limit of the function doesn't exist, but one-sided limit exists, right? One-sided. So this is called let's pick a different. So this is called right hand limit, and this is called left hand limit. Okay, very important theorem. If you ask why these one-handed limits are important, it's because of this theorem in some sense. So long story short, what it says is the original limit that we saw in the previous lecture. The original limit exists, so this is if and only if, right? If and only if both left limit and right limit exist. So what it means is following. If these two exist and equal, you see, LL, then this original limit exists, and vice versa. What is vice versa? If this limit exists, then we automatically know that left limit and right limit, they both exist and they are equal to L, the same L. Okay, so let's look at this picture and let's try to see what we can say. For example, what is the, you see, the function is defined only in here, right? So function is defined only from 0 to 4, right? So 0 to 4. So I cannot go beyond 4 or beyond 0. So for example, I can ask the following question, like what happens limit x, let's start from left, so from 0. So I want to approach from 0, but I cannot approach from left because it's not defined, right? Function not defined. So I can say what happens the limit as x goes to 0 from right of this function. So if I approach from right, my function is approaching to this point. So this is 1, right? Now let's approach to another point, 1. X goes to 1, f of x. Well, you see it has two different behaviors, so let's approach from left, right? If I approach this to this point from left, then my function is approaching to 0, right? It's approaching to 0. For function values, you need to look at y. So this is 0. Now, well, if I approach from right, so if you approach to 1 from right, then your function is moving here, so it's approaching to 1, right? So this is 1. So in particular, look at this the theorem. So you see, I'm approaching to 1 from left and left, so they are not equal, right? So it means, for example, I can now easily say that when x goes to 1 of f of x, it doesn't exist, DNE, right? It does not exist because those two limits are not equal. If they were equal, then I would use this theorem fix. I would say that, okay, it works. How about 2? Let's do the 2, right? So limit x goes to 2. Let's approach from left, f of x. If I approach from to 2, let me pick different color now. If I approach 2, my function is approaching to 1, right? So this is 1. Now, if I approach 2 from right, if I approach 2 from right, what's happening? So I'm moving here, again approaching to 1, right? This is also 1. So they are equal. Those two things are equal. What does that mean? This means limit as x goes to 2, uh, this exists and it's equal to 1. So it exists 1. You see? But what is f of 2? Be careful. What is f of 2? What is f of 2? At f of 2, I have 2, right? So you see, it's not equal, right? Limit of f of x equal to 1 is not 2, see? So you have to be careful. Although the f of 2 is 2, it's somewhere else, it's not 1, but limit is equal to 1, it's perfectly fine. So the limit of the function may be different from the value at that point. Let me repeat. The limit of the function at the point may be different from the value. Okay, so you have to be careful. Anyway, I don't have much space, so let me not write the others, but simply show you from here. So how about 3? Okay, it's okay, right? If I approach from both sides, I'm approaching to this peak, so it's 2, right? So it exists. How about 4? If I approach from 4, my function is approaching to 1, right? It's not approaching to this point, no. So limit as x goes to 4, but from left, I can't do from right, it's from left. This is equal to 1, right? Etc. Okay, now let's discuss this particular theorem. This is one of the important theorems. You will be using this later also, so you have to know this theorem. So this is theta is taken in radians, not in degrees. So what it says is limit as theta goes to 0, your sine theta divided by theta is equal to 1. Okay? So last time, if you remember, I told you, but haven't proved it, it was like an exercise for you that this is less than theta, right? It's less than theta, right? When, if you, right? Um, so from this, what you can do is, so let's say this is my proof, sort of. Um, it's so the book gives the geometric proof. You can also look at it. I'll use the part of it. But here, basically, this also means what? So sine theta divided by theta is less than or equal to 1, right? So I'm sort of trying to establish a sandwich theorem. But when theta is negative, this theta is also negative. So sine theta theta positive. When theta is positive, sine theta is also positive. So it's positive. So I don't need this absolute value. So I can safely say sine theta divided by theta is less than 1. So this is, let's call it star, right? This is one important thing. Later I will use it. So it's upper bound, right? So I know that the sine theta or theta is bounded by 1. Now I need to also bound from below, and then I will sandwich, use the Ascendance Theorem to show it. Okay. Now I go to geometry. So let's sketch this unit circle. Unit circle. Let's pick my theta somewhere here. It's close to 0, so it could be also here, but let's say 1. Uh, Now this radius is 1, so we know that this uh, side is equal to sine theta, right? We know that this is sine theta. Now let me continue with this line and look at this perpendicular blue one, the green one. So again, this length over here is 1. So what is then this side divided by this side is equal to tangent. But since this is 1, it means this part is equal to tangent theta, right? Tangent theta. So idea is to compare the area. So I can compare this small area. Let me pick a slightly different color here. If I look at this area of this sector, the sector area of the sector is it's theta r squared. So it's theta r squared over 2, but r is equal to 1. So this is theta over 2. And if you look at this, the area of this triangle, this particular triangle, clearly it's bigger, right? So it's bigger. But what is this, the area of this triangle, this green triangle? It's 1 times theta. So 1 times theta, sorry, tangent theta divided by 2, right? So let's go back to black. So this tells you what? This tells you that theta is less than tangent is sine theta over cosine of theta. So this gives you another bound, right? So which means cosine of theta is less than sine of theta divided by theta, right? So I kind of managed to find another bound. So let's call it double star. So now what happens if theta goes to 0? Then cosine theta goes to where? It goes to 1. Why it goes to 1? Well, okay, so you can do so the fact limit as theta goes to 0, cosine theta goes to 1. Cosine 0 is, because cosine 0 is 1. But I'll come to that fact. But bearing in mind this fact, so then uh, so by star by double star, right, if I use this 2, and also I use this fact, and I use the sandwich theorem, right, and by sandwich theorem, what do we get? We get that the sine theta over theta is sandwiched by 1 and this cosine of theta, but cosine theta going to 1, so from below it's 1, from above it's 1, so it means we established that the sine theta divided by theta goes to 1 as theta goes to 0. So this is another way of writing this limit theta goes to 0, sine theta over theta is equal to 1, okay? So you can also write in this form. So now let me quickly do what happens this fact. So let me erase everything. So this fact. Let me quickly do it. You can also do it by geometry, but I'm not going to do it by geometry. So fact is limit theta goes to 0 of cosine of theta is equal to 1. So what we know. So we already know the following, right? We know that last time we did this as theta goes to 0, sine of theta is equal to 0. So we did this part, right, last time. Well, for example, you can use the following. I mean, you can say like cosine square theta plus sine square theta equal to 1, right? We can use this identity, so which means cosine square theta is equal to 1 minus sine square theta, right? Now, this means if I take the limit as theta goes to 0 of cosine square theta, well, this is by this identity, it's just 1 minus limit of sine theta, right, as theta goes to 0, and then I can square by using limit laws. But sine theta goes to 0, so this is simply 1 minus 0, this is 1. So we see that cosine square theta goes to 1. So it means cosine theta goes to 0, wait, sorry, cosine theta goes to 1, or cosine theta goes to minus 1, right? Because cosine square of something goes to 1 means itself needs to go 1 or minus 1. But what is theta? Theta is close to 0. When theta is close to 0, which means it's like could be positive but very close to 0, or negative, so it means I'm on the fourth quadrant or first quadrant. In either quadrant, cosine is positive, right? So when this is cosine is positive, so this cannot happen. Okay, it means cosine theta goes to 1. Okay, let's do some examples. So one of the standard examples of using this theorem is the following. So find limit as x goes to, okay, let's use x. I mean, you can also use theta, but x goes to 0 of, I can say like sine 4x divided by sine 7x, right? Fine. Okay, what can you do? We know sine 4x over 4x goes to 1. We know sine 7x over 7x goes to 1. So we just imitate it, right? So we put this into that shape. So let me start with sine, with the original function. Then let me write what I said, right? So I write this sine 4x divided by 4x. And then I need to multiply by 4x, right? To accommodate this 4x. Similarly here, you write sine 7x divided by 7x. Then multiply by 7. Then nothing changed, right? You simplify 4, 4, 7, 7. Okay. But now this goes to uh, what? Where it does, where it goes? It goes to 1 because x goes to 0. Then 4x also goes to 0, right? Times 4x goes to something like that, right? So it's close. Let's say close. And here it's close to 1. Here it's 7x. But x is cancelled, right? Let me repeat different color. So this cancels. So which means this goes to 4 over 7. So you see, I didn't let x go to 0 x immediately because this will be like 0 over 0. It would make it doesn't exist, but that's not true. First you cancel, you simplify, as much as you can, and then you take the limit. Okay, so here I'm taking limit here, right here. Okay, one last example. Um, let's try to compute x goes to 0 of tangent of x. Let's use secant of 3x divide by, let's divide by, let's say 4x. Okay, so here you can write tangent of x as what? As sine x over cosine x, right? Over cosine x multiplied by, so you can write secant x as 1 over cosine 3x, and then we also have 1 over 4x. So we know sine x over x is 1, so this will take care of this denominator x, right? That's sort of one problem of, so we can avoid this problem by letting sine x over x, and then we get 1 over cosine of x times 1 over cosine of 3x, and also we have 1 over 4. So now we can evaluate, right, using the product rule of the limits. Sine x over x, because x goes to 0, this is 1. Be careful, I mean, sine x over x goes to 1 only when x goes to 0. If x goes to somewhere else, it's not 1 anymore. What is cosine of x? Well, cosine x goes to 1, so this is like 1 over 1. And cosine 3x, okay, it also goes to cosine 0, so it's also 1 over 1. Here is 1 over 4. So the answer is 1/4. Okay, so I'll stop here.